Hello. In this video, I'm presenting the results of a mathematical investigation into the effects of the position and movement of the Sun in a flat Earth theory. I say a flat Earth theory because there doesn't seem to be a consensus on what flat Earth actually means. In this exploration, I'm going to state which hypotheses are part of the theory under consideration. Firstly, we have the fundamental hypothesis of flat Earth theory, that is, that the mass of the Earth sits atop a flat plane. We will call this the Earth plane, and this hypothesis the Earth plane hypothesis. The second hypothesis concerns the position of the Sun in relation to the Earth plane. That is, that the Sun moves about in a plane that is parallel to the Earth plane and some distance above it. We will call this plane the Sun plane, and this hypothesis the Sun plane hypothesis. Before we proceed, I should issue a warning. We're going to be talking about observing the Sun, but it's vitally important that you do not stare at the Sun. You could do irreparable damage to your eyesight. In this section, we're going to look at how the position of the Sun on the Sun plane changes the viewing angle seen by an observer at some fixed point below the Sun plane. Here is the Earth plane, and here is the Sun plane, some distance above it as per our hypotheses. For our analysis, we shall consider an observer at some point above the Earth plane at a fixed distance, hs, below the Sun plane. The Sun is going to be a variable distance, ds, from where the perpendicular hs intersects the Sun plane. We shall also assume that photons travel directly to the observer along the path dp to create the observation of the Sun in the observer. This then creates a right-angled triangle of sides hs, ds, and dp. Theta is the angle from the perpendicular, hs, to dp, and what we would like to know is how theta changes with the distance ds. This is easily found using trigonometry, in this case using the inverse or arctangent function. If we examine the arctangent function, we know that as x approaches infinity, theta approaches 90 degrees. We can see from our formula that, since hs is fixed, as ds approaches infinity, then xs also approaches infinity, and thus, as ds approaches infinity, theta approaches 90 degrees. But what about the values of theta when ds is less than infinity? In order to calculate a set of values for theta, we are going to use the GNU Octave numerical computation tool. The first thing we need for our computations is a value for hs. What we're going to do in this analysis is assume that hs is 1 and generate other quantities from hs. For example, we use this octave function to generate 101 values between 0 and 100 times hs. Since hs is 1, we generate this set of numbers, which gives ds as a value in terms of hs. That is, the first number represents a distance of 0, the second a distance of 1 hs, the second 2 hs, and so on. Now we have a value for hs and a set of values for ds. We can get Octave to calculate the corresponding values of theta for each of these ds values. To visualize the result, we can use Octave's graph plotting feature, which gives us this result. Note that when ds is only 5 or 6 times hs, the Sun is already at 80 degrees from the vertical, 10 degrees from the horizontal. But it must be a great deal further away in order to get close to the horizontal eye level. When ds is 100 times hs, the angle is still more than half a degree from the horizontal. 1 degree is achieved in the upper 50s and 2 degrees in the upper 20s. Given that casual observations indicate the Sun coming close to horizontal eye level, this is a potential problem for our hypothesis, especially with larger values of hs, say 1000 kilometers. Another property of objects as they move relative to an observer is a perceived change of size. We're going to use Octave to generate values for this perceived change as the distance ds changes. As before, we have our triangular relationship, but now we're interested in the angular size of the Sun. To calculate this, we need to know the diameter of the Sun. I believe that this formula calculates the angular size of a sphere at a distance from the observer. We can easily calculate dp from hs and ds using Pythagoras' theorem, and we will assume that the diameter of the Sun is 1/10 of hs. We can now get Octave to calculate and plot the angular size as ds changes. There is a very sharp drop-off in angular size as ds increases. Note that the x-axis is identical to the previous plot, and in the upper 20s, where the Sun was 2 degrees above the horizontal eye line, the angular size is an order of magnitude smaller than the size when it is directly overhead, and gets smaller still as ds increases. This implies that as the Sun appears to get closer to the horizontal eye line, it must also dwindle to a point like a star or a planet. Let's look at another property of the Sun that should change with distance, namely its brightness. We start again with our triangular setup. We assume that there is maximum brightness when the Sun is overhead, that is, ds is 0, and we call this BP max. The brightness of the Sun at a distance ds is BP. From what I can tell, changes in the brightness of the Sun follow an inverse square law, hence we can find BP using this formula. dp squared is easily found using Pythagoras, so here is the formula we want to explore with Octave. And here is the resultant plot. Again, the x-axis is the same as the previous plots. We see a very rapid drop-off in brightness, such that it is only a couple of % of the maximum once ds is 10 times hs. This means that it should be quite dark before the Sun could be observed even 2 degrees above the horizontal eye line. So far, we've looked at the relationship between the Sun's position on the sun plane and various properties perceived by an observer. In this section, we will look at some angle and distance relationships in the movement of the Sun with respect to a specific event, namely the phenomenon known as the equinoxes. For this analysis, we require some observational data, which we're going to take from the Solar Electricity Handbook. In particular, the site maintains a calculator for the angle of the Sun for the purposes of efficient orientation of a solar panel. Here, we can see the data it provides for the tilt angle of a panel for each month of the year in Asiat, Greenland. It's quite easy to check that the angle of tilt is the same as the angle of the Sun above the horizontal. Since we are interested in the equinoxes, we will be using this data point in the calculations that follow. Note that we assume this data is correct based on its utility to the users of solar panels. Here we see Asiat in relation to the Earth plane and the Sun plane. We suppose the existence of a point E directly below the Sun at noon on the days of the equinox at the same height, hs, from the Sun plane. As before, we can construct a triangle between Asiat, E and the Sun. Since we know theta from the solar panel data, we can calculate the distance dA through some standard trigonometry. This evaluates dA to be about 2.61 times the height hs. Now, we're going to change our point of view of this relationship and look down on the Sun plane. In this view, we see Asiat and E, and we assume that the Sun, when it appears in the morning of the equinox, is directly due east of E. Between these 3 points, we can again construct a right-angled triangle, using dA, which we just calculated, and our assumption about the trajectory of the photons from the Sun to the observer. At the equinox, the Sun appears due east to all observers. This means that theta in this triangle must approach 90 degrees in order for an observer in Asiat, for example, to experience an easterly appearance of the Sun. We could apply our calculation approach to determining ds values to achieve such an observation, but we've already effectively done this because this is exactly the same calculation that we did in section 1. Only this time the value for the adjacent side is 2.61 times hs, meaning that the graph stretches out over a greater range of values to get the same angles. For example, to get to 80 degrees, we must have ds exceed 15 times hs rather than the 5 to 6 times that we saw in section 1. To reach 88 degrees, ds needs to be in the upper 70s times hs, and at 100 times hs the angle is still 1.5 degrees off due east. 89 degrees is reached when ds is about 150 times hs. Since we assumed that the sun is physically due east of E when it appears in the morning, that is directly overhead at noon, and is physically due west of E when it disappears, then this implies that the sun might have to travel 300 times hs in the 12 hours between appearance and disappearance, and would still be 1 degree off our due east-west observation of the sun in Asyut. This puts quite a strain on the sun plane hypothesis, particularly as hs, the height from the sun plane to the observer, gets larger. It also causes problems for the analyses in sections 2 and 3. In this final section, we're going to examine the monthly changes in the noon position of the sun and how it is experienced by 2 observers. Using the solar angle calculator again, we get data for Plymouth in the UK. For this analysis, we're interested in the angles between the June solstice and the December solstice. Our second observer is in Abidjan, Côte d'Ivoire. These 2 places were chosen because Plymouth and Abidjan are due north-south of each other, and they are both on the same body of water, namely the Atlantic Ocean. This last fact is going to be used with a third hypothesis we shall introduce into our flat Earth theory. That is, that the surface of a body of water is parallel to the Earth plane. This means we can infer that Plymouth and Abidjan are the same distance hs from the sun plane. Here then are our 2 observers, both observing the sun and forming triangular relationships in the way we've already seen. In this analysis, we're going to look at how the theta angles change each month and how that correlates with changes in the corresponding position of the sun for each of the observers. We start by calculating the value ds for each of the observers for each angle to the sun using simple trigonometry. For Plymouth, we get these values. Remember that these are multipliers of hs. From June to December, the position of the sun is in the sky must move about 3 times whatever hs is. For Abidjan, we use a similar calculation and obtain this set of values for ds. In this case, the sun only changes position by about 1 times hs from June to December. This is inconsistent with the values calculated for Plymouth. To see this more clearly, we shall normalize each dataset with respect to their June values and plot them side by side. On the left, you can see how ds must change in order for the observer in Plymouth to experience the noon sun angle dataset, and on the right, how ds must change for an observer in Abidjan in order that they experience the noon sun angles reported in that dataset. These are clearly inconsistent with each other. They would have to be observing 2 different objects in the sun plane, but our hypothesis implicitly supposes only one such object. Let's add a third observer in Malaga, Spain. This is between Plymouth and Abidjan and is on the Mediterranean, which directly connects to the Atlantic, allowing us to deploy the water level hypothesis again. If we carry out the same analysis on this dataset and add that to the plot, we see a different set of changes in ds are required to be consistent with the Malaga angle dataset. Let's take a different approach to analysing this angle data. In this case, we will strongly assert that the sun plane hypothesis is true. We will assume that the June values for both Plymouth and Abidjan are correct and are from observations of the same object. We will also assume that changes in the sun position from Abidjan are the correct ones. Using these assumptions, we now calculate the new ds change values for Plymouth. Assuming that the Plymouth angle data is correct, we now use basic trigonometry to calculate the required height hs for the new ds values to be consistent with the Plymouth angle data. That yields this set of values for hs. In June, hs is 1, as we would expect from our assumptions. And as we move through the year, we get progressively smaller, and this means Plymouth must be getting closer to the sun plane each month, while Abidjan remains at the same distance. So, what can we conclude from these numerical investigations? Section 1 implies that the Sun has to be a large multiple of the distance hs to get within 1 degree of the horizontal eye level. If we add to this the results from section 2 and 3, we find that at such a distance the angular size of the Sun would have dwindled to a point, but also it would have long ceased being visible to an observer due to a massive reduction in brightness. Section 4 also implies that the Sun must be at a great distance from E in order that observers in other parts of the world also experience an easterly appearance of the Sun. In the case of Asyut, 150 times HS was still 1 degree off a due east appearance. This makes the results from section 2 and 3 even more of an issue. Finally, section 5 indicates either the sunplane hypothesis or the water level hypothesis is false. In the face of the assumptions, data and calculations presented, a flat Earth theory cannot contain both the sunplane hypothesis and the water level hypothesis. Thank you for watching. Any relevant comments, questions or corrections can be put in the comment section below.